Read complexity straight from the code. We've already learned what big O notation means and walked through the 6 classes. In this video, you'll learn how to look at a piece of code, any piece of code, and find its big O in a few seconds. By the end, reading complexity will be as automatic as reading English. Data structures and algorithms foundations. Reading complexity from code. Here are 5 small functions. Each one is short, just a handful of lines. But each one belongs to a different big O class. By the end of this video, you will read all 5 at a glance and tell me their complexity without thinking. Let us look at them first. A simple for loop that prints every item in the list. One pass, very common pattern. You write this every day. B, 2 nested for loops, comparing each item to every other item. Looks innocent, it's not. This pattern shows up everywhere in interview problems. C, a while loop that splits the search range in half each step. This is binary search, one of the most important algorithms in computer science. Notice the structure. D, a recursive function. Factorial of n. Returns 1 if n is small, otherwise n times factorial of n minus 1. Single recursive call per step. E, another recursive function. Naive Fibonacci returns an if small, otherwise the sum of 2 recursive calls fib of n minus 1 plus fib of n minus 2. 2 recursive calls per step, that's the key difference. 5 patterns, each one in a different complexity class. We will look at each one, find its big O using a simple recipe, and at the end we will come back to all 5 together and verify the verdict. Algorithms plus data structures equals programs. Niklas Wirth wrote that in 1976. It became the title of one of the most influential programming books ever written. The insight is deep. When we read code, we are really reading 2 things at once. The algorithm and the data structures it uses, and big O depends on both. Choose the wrong data structure, and even a clever algorithm becomes slow. Pay attention to both halves. The recipe, 3 rules. With these 3 rules, you can find the big O of almost any piece of normal code. They aren't complete, there are edge cases, but they handle 90% of what you'll see in practice. Rule 1, count nested loops. Every level of nesting over the input adds a factor of n. 1 loop is O of n. 2 nested loops is O of n squared. 3 nested loops is O of n cubed. The depth of nesting directly maps to the exponent on n. The fastest way to spot quadratic code in review is to count opening braces inside the loop body. Rule 2, if a loop or a recursion throws away half the input on every step, the depth is log base 2 of n. Halving is a log. This is the single most important shortcut. Whenever you see something dividing by 2 or splitting in half, suspect a logarithm. Rule 3, a hash lookup is constant. A dictionary lookup, a set membership check, a hash map insert, all O of 1. If you can replace a search loop with a hash lookup, a full factor of n disappears from your complexity. That single trade is the foundation of most make this faster optimizations in interview problems and in real systems. Pattern 1, a single loop. For x in R, print x. The simplest possible loop pattern. This is 1 pass through the list. The loop body runs n times, once for each item. Each iteration does constant work, just a print. Total work is n times 1, which is n. That gives us O of n. Linear time, apply rule 1. 1 loop equals 1 factor of n. Done, this is the baseline pattern every other one builds from. Pattern 2, a nested loop. For I in R, for j in R, compare E and j. Looks slightly more complex, but should now be easy to read. Apply rule 1. The outer loop runs n times. For each of those, the inner loop also runs n times. The total work is n times n. That's n squared. That gives us O of n squared. Quadratic time. Watch for this pattern in code review. It is the single most common scaling problem in real code bases. 2 nested loops over the same data is a serious problem when n gets large. Pattern 3, halving the input. This is the canonical binary search. We have a sorted array and a target value. Each step, we check the middle element. If the target is smaller than the middle, we search the left half. If it is bigger, we search the right half. If equal, found. Apply rule 2. Each step throws away half the remaining range. We start with items. After step 1, n over 2. After step 2, n over 4. And so on until we are left with one item. The number of times you can halve n down to 1 is log base 2 of n. That's the depth. So binary search is O of log n. Logarithmic time, doubling the input only adds one more step. This is the complexity class that lets you search 1,000,000 items in 20 steps and 1,000,000,000 items in 30. The magic of halving. Pattern 4, linear recursion. Factorial of n returns 1 if n is small, otherwise n times factorial of n minus 1. Recursion that calls itself once per step. Each call does constant work, just one multiplication and one comparison. And it calls itself once on a smaller input, specifically n minus 1. So the depth of the recursion is exactly n. N calls total, each doing constant work. So this is O of n. Linear time, just like the single loop, but expressed through recursion instead of iteration. The pattern to remember, recursion with one self-call per step, is linear, not exponential. Don't be scared of recursion. The branching is what makes it expensive, not the recursion itself. Pattern 5, branching recursion. The naive Fibonacci function. It returns an if n is small, otherwise it calls itself twice, once on n minus 1 and once on n minus 2. The key word is twice. Each call branches into 2 recursive calls. Each of those branches into 2 more. The recursion is now a binary tree, not a single chain. The depth of the tree is roughly n. So the total number of nodes, the total number of function calls, is roughly 2 to the power n. Computing fib of 50 in this way takes over 10 to the 15 calls. To put that in perspective, that's more calls than there are seconds in 50 million years of computation. The naive recursion computes the same numbers again and again throughout the tree. Fib of 48 gets recomputed billions of times. So naive Fibonacci is O of 2 to the n. Exponential, almost never acceptable in real code. The fix, memorize the results, or compute bottom-up. That turns it into O of n. We'll see those patterns when we cover algorithm design later in the series. Now here is the most important trick for reducing complexity in everyday code. The lookup trick. Same problem, 2 different complexities depending on the data structure you choose. This is the trick that turns interview rejection into interview offers. Version A, 2 nested loops looking for a pair of numbers that adds up to a target value. The outer loop picks one number. The inner loop searches for its complement. That is O of n squared by rule 1. Version B, walk the list once. For each number, check if its complement is in a hash set. If yes, return true. Otherwise, add the current number to the set and continue. The set lookup is O of 1 by rule 3. The full loop is O of n. Same problem, same correctness. A factor of n disappears just by choosing a hash set instead of an inner loop. This is the single most useful pattern in interview problems and in production code. Whenever you find yourself writing a nested loop to search inside another loop, ask, could a hash do this instead? Almost always, yes. Now let us return to the 5 functions from the start. Each one demonstrates exactly one of our patterns. Let's walk through the verdicts. A, the single loop is O of n. Apply rule 1. One loop, linear. B, the nested loop is O of n squared. Apply rule 1. 2 nested loops over the same input. Quadratic. C, the having while loop, is O of log n. Apply rule 2. The search range halves each step. Logarithmic. D, linear recursion, is O of n. 1 recursive call per step. Linear depth, linear total. E, branching recursion, is O of 2 to the n. 2 recursive calls per step. Exponential, the slowest of the 5, by a wide margin. A quick reference to take with you. 6 common code patterns and their complexities. Screenshot this slide, print it out, tape it to your monitor, whatever you need. Direct access, an array index, a dictionary lookup, is O of 1. Constant time, direct jump, no iteration. Halving loop or halving recursion is O of log n. Binary search is the canonical example. Anything that throws away half the work each step gets a logarithm. A single loop over the input is O of n. Sum, filter, scan, all linear. The bread and butter loop you write every day, sort, then scan, is O of n log n, the price of any general purpose sort. If your algorithm starts with first, sort the data, your complexity floor is n log n. A nested loop over the same input is O of n squared. Watch for this in code review. The single biggest source of slow production code. Branching recursion to a more recursive calls per step is O of 2 to the n. Exponential, almost always a sign that we need memoization or dynamic programming to bring it back down. Save the slide. You can now read code. The next time you see a loop, ask one question. How does the work grow with n? That's the entire skill. The rest is recognizing patterns. Loops over the input multiply your complexity by n. Halving divides by log n. Lookups are constant. And branching recursion is exponential. Watch for it more carefully than for anything else. Most production performance bugs are nested loops or branching recursion that didn't get noticed in review. Space complexity is coming in future episodes in this playlist. The other dimension of complexity, because a function can be fast and still run out of memory, and most engineers think about space only when they need to. Smart data structures and dumb code works a lot better than the other way around, Linus Torvalds, which is exactly what the lookup trick proves. The right data structure removes the need for clever code. A hash set turns nested loop quadratic into single loop linear. The lesson: choose your data structures carefully and the algorithms get simpler. Thanks for watching. If this video helped you read Big O straight from code, please like, subscribe, and leave a comment below. Tell me which pattern was the most surprising for you, or which one you've seen in your own code base recently. More on space complexity and algorithm design is coming in future episodes in this playlist. See you there.